how visual stimulus can affect our sense of touch in virtual reality. So this should be able to apply to a lot of different fields. However, we've been focusing on how it could apply to phantom limb pain treatment. So I want to give you a little bit of context into what phantom limb pain is before we get into the actual experiment. So phantom limb pain is a neuropathic condition, and it's when someone has an amputation and they can still feel the limb. However, that limb can feel very, very painful. It can feel cramped, they can feel extreme temperatures, it can feel itchy. It's quite an awful experience, okay? 90% of upper limb amputees will generally get phantom limb pain, so it's quite a prevalent condition. So to give you a general understanding about how it emerges, we don't yet understand exactly the main causes. However, a lot of experts they have some sort of consensus. So in a normal non-amputee, the limbs and the brain will constantly communicate, unconscious or consciously, and there will be afferent and efferent signals being sent to the limb and back to the brain, saying things like, what position is it in? What am I sensing? Am I touching things? Because that's the main functions of a limb, is to know where it is in space, to sense the environment, and to manipulate the environment. However, in an amputee, these afferent and efferent signals are disrupted. There is no longer any afferent signals going into the brain saying this sort of information, and any efferent signals that are going to the limb are being kind of lost in translation. And this disruption can cause a lot of confusion and can lead to pain, okay? So pharmacological drugs, surgery has been quite ineffective. There are some surgical procedures like TMR that have shown some good traction. However, they're not really accessible to a lot of amputees. So in 1996, Ramachandran created the mirror box therapy. And in mirror box therapy, someone will put the intact limb in front of a mirror, and their reflection is superimposed onto the phantom limb. And so someone can actually move the limb around, and this superimposition will make it look like the phantom limb is moving in a predictable way. And a clinician can sometimes go in and manipulate the hand, so massage it or scratch it, in order to alleviate this pain or discomfort that the amputee is feeling. Now, the premise of this is visual capture. And visual capture sort of is a phenomena where vision takes precedent or dominates many other modalities such as taste, tactile sensation, and auditory signals. And we put a lot of weight into the vision, and so what we see is sometimes what we feel or hear instead of what the reality of the situation is. Now, this principle is when you see something, you can then have a cross-modal interaction, and this can reintroduce tactile sensation, kinesthetic, and proprioceptive modalities back into the part that is not being affected anymore within the brain, specifically the somatosensory cortex and the motor cortex. And by doing this, you reintroduce the modalities and then it alleviates the pain. That's the general principle of this. There are some key issues with mirror box therapy though. It's very inaccessible to a bilateral amputee. So a bilateral amputee is when they have both arms that are removed, because he can't reflect a limb anymore. You may think, well, you can get someone else to reflect the limb instead. If they cannot embody that limb, then the treatment doesn't seem to work, okay? Also, for upper limb amputees, it's very, very hard to self-medicate. I don't want to use medicate too much, but you can't do things like stretch or scratch the limb because your arm is being reflected, and so you can't self-scratch your own limb. So it's very, very inaccessible to upper limb amputees if you're trying to do it by yourself. We have got some solutions. There are some VR applications. They are quite fragmented though. As I said, there are two different frames. There's the proprioceptive and kinesthetic applications, and then there's the tactile. Now, we've created lots of VR applications that will take the muscle input and then recreate the limb visually, and the amputee can then move this virtual limb in a way that they would like to. Now, there's a lot of issues around this. Some really good researchers are looking into how we can better this. However, we have got these options. there's been a lot less work in the tactile situation. People like Sano from the University of Tokyo, they've been using vibrotactile sensations on the face, and I'm not going to go into this in too much detail, but if you touch the face for a lot of upper limb amputees, they can feel it on their phantom limb. And they've been using vibrotactile sensations to reintroduce some sort of tactile sensation on the phantom limb. This phenomena is not ubiquitous for every single amputee, though. Only about 10% of amputees, upper limb amputees, can actually feel this sensation when being touched on the face. So we need to find a different way of stimulating some sort of tactile sensation for these amputees. So the current gaps in knowledge is little vibrotactile sensation, and there's very little looking at the predictability of it as well. So what I'm trying to do is I'm trying to take some principles from the rubber hand illusion and use it for my application. So the rubber hand illusion is a psychological phenomena that you can embody a limb or an object and think of it as your own. And what they use is synchronous and congruent sensations for you to embody this limb and then feel it on your own limb, even though it's not being touched in any way. Now, this has been recreated in virtual reality, but I would like to use it for a different method. This is just a phenomenon, not a treatment. Okay? So our aim is to investigate whether a passive tactile perception can be relocated distally towards the fingers and forearm or contralaterally to a different side of the arm by an innocuous visual cue that is being associated to a decoupled visual vibrotactile stimulus. So to get into methodology, we recruited 16 participants, 10 of them are female and 6 male. All participants were non-amputees because we wanted to find a baseline and a fundamental purpose of the VR. The age range was 25 to 57. 13 people were right-handed, 2 were left-handed, 1 person was ambidextrous. We'll get into why that sort of thing is quite important later on, though. So, the methodology. Participants viewed virtual arms using the leap motion, and the application was created in Unity. They were textured in such a way that it divided the arm up into separate sections throughout the arm. Vibrotactile actuators were put onto 4 places, 2 on each arm. So as you can see, the red dots, that's where the vibrotactile actuators were placed. They were measured through anatomical landmarks on the arm to make sure it was consistent between participants. And they were issued a series of lights and vibrations. The lights you can see just above the rings or below the rings. And these were decoupled. We'll talk about that a little bit later. And we asked them to verbally state where they felt the vibrations, not where they saw the lights. The lights were luminous icosahedrons with a luminosity of 4.8 centimeters that radiated throughout. The vibration modules were set to the receptive fields within the arm and the forearm. Just to make a note, that the sizes of both of these lights and vibrations fit within the sections. So the sections were split up into the receptive fields for their appropriate section. The vibration and lights were shown for about 1 second, and the hertz, 230 hertz and 1.2 grams of amplitude for the vibration modules. We had 6 phases, so this was a repeated measures experiment. We'll go into this in a little bit more detail, but every single one, so just to give you an idea, the control was just to see where the location the vibration was on the virtual arm. The rest of them are to decouple the visual stimulus and the vibration stimulus, and the others were to try to recreate some of the findings that we found in mirror therapy and virtual mirror therapy. The expectation phase was to mirror stuff from the rubber hand illusion. Okay, as I said, we'll go into this in a little bit more detail. We used a Latin square approach to counterbalance each of the vibrations and other vibrations. 16 trials were put out altogether. We further counterbalanced by switching the disruption 1 and 2 because we didn't know if there would be an effect between presenting the light contralaterally or distally at some point. So, our results were first off visualized like this. We used projection mapping onto the hands. However, this wasn't publication friendly in any way. We could not fit in all the information onto one piece of paper. So we used a grid-based system, kind of like this, that matches. And that allowed us to be able to easily compare between the two different ones. Okay, so each part will represent part of the hand. So just to go on to the results, I'm not going to go through this in too much detail. The controls, they centered around the vibration module. There were no lights in this condition. However, most of the participants could identify where the vibration module was, even though they couldn't see the vibration module. When we went on to the association phase, where the light was turned on, close to where the vibration module was, we did see quite a dramatic shift towards the visual stimulus, especially on the right forearm, where there was now a bimodal distribution between the actual source of the vibration module and where the light was. We did reiterate every single break phase. Oh, sorry, didn't say about the break phase. We issued a break phase within each of the conditions to make sure we can manage fatigue and to know that they were stating where the vibration was instead of just stating where the light was. And so we can see that half of the participants or the responses was going for the light. Within disruption 1, there was a redistribution around the central line. We didn't have too much of a shift, but it was quite significant in a way. For disruption 2, this is where the light was distally shifted down the arm. We did have a shift towards the light, so from the forearm to the hand, which was quite important because this is what we want for a treatment purpose for mirror therapy. We haven't got any images for expectations, but when the light was present and no vibration was present, none of our participants said that they felt a vibration in any way. And for our control, the post-control that we had, a lot of the results centered around the same place as the initial control. So just to summarize the results, tactile sensation seemed to be localized around the site of the vibration module. However, there was a large distribution for the vibrations. This meant that the vibrotactile sensation that we produced wasn't localized in the exact place that we put it. So in a lot of research and papers that we've read in HCI sort of research, they generally only talk about the exact place. So if the vibrotactile sensor is about 1 centimeter, they'll only talk about the 1 centimeter range around it. However, what we've seen is we can have variations from up to 4.8 centimeters away from the actual site of the vibration module. A lot of what we found was proximal to the visual stimulus. So if there was a close distribution between let me rephrase. If the visual stimulus and the tactile sensation was very close, we saw a very, very large difference in responses. However, the further the visual stimulus was away from the actual vibration stimulus, it was a little bit more divergent. Do you need time? The vibrotactile stimulus was not always evident every single time. So throughout the actual experiment, they were not always very, very accurate. Sorry. If we wanted a very, very granulated and accurate measurement for the vibrotactile stimulus, I think using 2 motors may be a little bit more important because we can use things like the cutaneous rabbit illusion and phantom sensations, which is a little bit more granulated than what we found. It was also really important, the leap motion, if we include an elbow joint, the participants could identify whereabouts on the arm was a lot better than what we've just had with a disembodied forearm joint. So if we really want very, very localized tactile sensations, I think including an elbow joint would be very, very beneficial. We couldn't recreate all the findings from mirror box therapy in any way. However, we did find that allowing a visual stimulus to be present while a vibrotactile sensation was present we could shift the vibrotactile sensation down the arm, which is very, very promising for phantom limb pain treatment. We didn't have a large response rate. This may have been because the visual stimulus wasn't congruent enough. The light doesn't really equal a vibrotactile sensation. Or it may have not been excitable enough. If we had a little bit more congruency between that, so like stroking, we may have had a bigger impact. It also may be very, very different for amputees. So we know that amputees' brains have very, very different properties than non-amputees, and they could be a little bit more susceptible to vibrotactile sensation relocation than non-amputees due to the shrinking of the somatosensory cortex. I'm not going to go on to that, but we have got some further research. A lot of our work at the moment is preliminary data, and there's a lot more to look into. Mainly, I would like to be able to try this sort of application with amputees at some point to see if we get different results. Thank you.